Okay, so we had sine x show up, and then did you see any graph that was different? No, it overlaps completely. Okay, so we can say that the two graphs are identical. At this point, we can. Pardon? So this graphed sine x, and then y2 is tan x cosine x, and it graphed the exact same line. If I took y1 out, you would see that as well. Okay, so it's giving the graph of sine x. We just need to graph that now. Sine x starts at the origin. Emily, did you get something different?
I just didn't do the brackets, that's why.
Oh, okay. Okay, so right now these graphs appear to be identical. Okay, but as we know, the right-hand side had a restriction, the left-hand side did not. So we're just going to play with a few values that we're going to sub into f of x and g of x and just see if there are actually any restrictions. So based off of those graphs, let's evaluate sine of pi over 2. That's f of pi over 2. Okay, so sine at pi over 2 is right here. What's the value going to be? It's positive 1. Okay, then let's calculate tan pi over 2 times cosine pi over 2. Okay, because g of x is tan x cosine x. Okay, g of x is tan x cosine x. So when you calculate that, what do we get? Does it work? You'll probably get that you have an error or it's undefined. Let's just talk about that. Okay, do you guys recall the graph of tan? Looks like this, and had some vertical asymptotes. Well, its first vertical asymptote occurs at pi over 2, 90 degrees. So if tan pi over 2 is undefined, then all of g of x is undefined. Okay, so that means we have a restriction. And if there's a restriction here, there's also a restriction at pi over 2 on this graph. Okay, and I'm supposed to draw it down here, but I'll just draw it up here. Okay. So at pi over 2, we actually have a hole in the graph. There's a restriction. It's undefined there. Let's test a few more points. So sine 3 pi over 2. Okay, we go through at 180 and then at 270 or 3 pi over 2, we're at negative 1. And you can just calculate that on your calculator. So sine 3 pi over 2, you should get negative 1. So it exists for f of x. Let's see if it exists for g of x. So we're going to calculate tan 3 pi over 2 times cosine 3 pi over 2. Okay, looking again at tan, where are the restrictions? Starts at pi over 2, and then every period, so 180 degrees or pi radians, you're going to have another restriction. So 90 plus 180 is 270, or 3 pi over 2. We have another restriction for tan 3 pi over 2. And if you try to calculate this, your calculator won't let you. It'll say error. So this is also undefined. Okay, so at 3 pi over 2, which is roughly here, okay, we're going to have another hole. Another point of discontinuity. Got that, Bruce? So So the left-hand side of the identity, sine x, no restrictions, but the right-hand side, tan x cosine x, because we had the identity tan x changed to sine x over cosine x, and we had a denominator here, that means that we have a restriction on the denominator, so we cannot divide by 0. So just to put that together, if you guys go second cosine 0, what do you get? So if you're in degree mode, you'll get 90 degrees. If you're in radian, you should get pi over 2. So kind of like our reference restriction is 90 degrees. And then every 180 degrees, we have another restriction. Okay, and I'll just draw a little picture of cosine, help you see that a little bit. So, back a few lessons when we were learning about the solutions of cosine and sine, we looked at the x-intercepts. Now, if we were just to look at the graph of cosine x, when that equals 0, we have our x-intercept. Okay, and the solutions there were pi over 2 and 3 pi over 2, or 90 degrees and 270 degrees. So if the solutions of cosine x equals 0 is pi over 2 and 3 pi over 2, then the restrictions when cosine x can't equal 0 are the same. They're 90 degrees and 270 degrees. Okay? So we just have to look at the graph of cosine, set it equal to 0. Whatever the solutions were, those are now your restrictions. And they occur every 180 degrees. Okay? So if we're going to summarize, okay, the identity sine x is equal to tan x cosine x, okay, but we have restrictions. And those restrictions would be x cannot equal 90 degrees plus 180 times n, okay, or pi over 2 plus pi n, where n is an integer. Okay, so we can say that this identity is true, but we also have to state the restrictions on the identity. Okay, now if you want to get a better picture, sometimes if you are in degree mode and you're using zoom trig, you can get a better image and you can see that hole in the graph. But sometimes you can't, so it just depends on your calculator. If you want to change to degree mode and test it out, see if you can see that hole, you can, or you can just look at the denominator and then find your restriction. Okay, so it depends how you want to use your time. If you do have extra time, you can, but I wouldn't. Okay, so when are we going to find these restrictions or non-permissible values? It's going to be when we look at tangent, cotangent, secant, or cosecant functions. And that's because we're going to have denominators. So for example, if we have tan x, the quotient identity is sine x over cosine x. We can't divide by 0, so here, cosine x cannot equal 0. Secant x is a reciprocal identity, giving you 1 over cosine x. You can't divide by 0, so cosine x cannot equal 0. Okay, so that's going to be non-permissible values for cosine x equals 0. Okay, and then cotangent, if we take the reciprocal of the quotient identity here, we get cosine x over sine x. So now sine x is our restriction. Sine x cannot equal 0. Okay, and cosecant is equal to 1 over sine x. Again, sine x is in the denominator. We can't divide by 0, so sine x cannot equal 0. So basically you want to find the solutions for cosine x equals 0 or sine x equals 0, and whatever those solutions are, the general solutions, that's going to be your general restrictions. Okay, all in all, if you have a denominator, you will have a restriction. So one thing to probably memorize if you can, for sine, the solutions, I'll just draw a little picture underneath here. So for sine, this is the general graph. For sine x equals 0, we have x-intercepts at 0 degrees, 180, or pi, and 2 pi. So if those are our solutions, then if that's in the denominator, they'll be our restrictions. And to summarize this, every pi radians, you see a solution. So sine x equals 0, the solutions would be n pi, where n is an integer. If we say had 1 over sine x, then we would say that x cannot equal 0, pi, 2 pi, basically every pi. So to summarize that, x cannot equal n pi. Okay, and then we also have cosine x equals 0. There's going to be solution starting at 90 degrees and then every 180 degrees. So pi starts at 1, or sorry, cosine starts at 1, works its way down and then back up. The solutions are at pi over 2 and 3 pi over 2. If you can't memorize it, just graph it, find the x-intercepts. Don't worry about it. Okay, but it will allow you to be quicker on these questions. Okay, so what if I had 1 over cosine x? Then I know that I have a restriction that cosine x cannot equal 0. And the solutions for cosine x equals 0 was 90 degrees, 270 degrees, basically 90 degrees plus pi n. So x would not be able to equal, well, it's already written here, okay? Pi over 2 plus n pi. And n has to be an integer. Okay, so it's worth memorizing if you can, just to save a step, but if you don't, you can just figure it out on your calculator. So when you're proving an identity, there's a few steps. It's recommended to solve the complex side first, but sometimes I find it's nice if one side is super easy, just to simplify that first, and then you know what your goal is, what you're trying to achieve. Okay, but if needed, just start on the complex side first. If you can, you want to use the identities that I've listed over here. So the basic identities, Pythagorean identities, reciprocal, and quotient. So try and use those first. Okay, whenever possible, change to sine and cosine. So you want to put things in terms of sine and cosine. For example, tan x can be written as sine x over cosine x. So if you can change it to those, do that. Step 4, factor if possible. And step 5, the sum and difference identities. We haven't looked at that yet, but we will look at those identities later. Okay. But sorry, this one's actually saying if you have a sum or a difference, basically you have to find a common denominator, combine those. Okay. We'll do a few examples to go through that. Okay, so for example 1 here, we have 1 over cosine x minus cosine x equals sine x tan x. So just looking at it, in your opinion, is the left-hand side more complex or the right-hand side? Left-hand side. So let's start there. We have 1 over cosine x minus cosine x. Okay, as recommended, you want to keep it in terms of sine or cosine. So you don't want to be changing this to the reciprocal. Leave it as is. Step 5, we can combine a sum or difference, and we'd have to use a common denominator to start. Okay, so first step, we need a common denominator. Cosine x, whatever you multiply in the denominator, you have to multiply in the numerator. So now both terms have cosine x as the denominator. And I can combine the numerators. I get 1 minus cosine x squared. Now, some of you might not recognize this right away, but the numerator is actually an identity. Can you guys get creative and try and figure out which one it is? So there's no cosine x squares, no cosine x squares. We have a cosine x squared. So how can we get creative with this identity?
Move this cos over.
Good. Okay. So we have sine x squared equals 1 minus cosine x squared. So we can rewrite 1 minus cosine x squared simply as sine x squared. Okay. So here we're going to use the Pythagorean identity, and you can rearrange them. Okay, so from there we get sine x squared over cosine x. And sorry, I did part C before A. We'll just switch the two, okay? All right, so now let's go to the right-hand side. We have sine x tan x. Which identity can I use? So I'm in terms of sine and cosine. Oh, quotient identity, good. Okay, so we have sine x, and then tan x will become sine x over cosine x. And then we just multiply through and we get sine x squared over cosine x. Left-hand side equals right-hand side. So we've proven our identity.
How do you, how would they ask you to do that on the diploma if you can't do short answers? How would you make a multiple choice question?
You probably have numerical response where you might have to fill in, maybe there's options or something, like they would have steps or something like this student solved this or proved this identity this way, which step did they make an error, or which is the final, like multiple choice. Basically they'd probably give you this identity and say, what does this simplify down to, or something like that.
Yeah, okay.
Now taking a look, sorry, we're just going to jump to part D here. So state the restrictions in terms of x. So what have we divided by? Okay, on the left-hand side, we're dividing by cosine x, cosine x, cosine x. So cosine x cannot equal 0. On the right-hand side, the only denominator that comes up is also cosine x. So cosine x cannot equal 0. I'm just going to remind you guys that if we looked at cosine x equals 0, the graph would look like this. And our x-intercepts, our solutions, would be at pi over 2 and 3 pi over 2. If we can't equal 0 now, that means that these values do not exist. Okay, pi over 2 and 3 pi over 2. So that means x cannot equal pi over 2. And if I'm talking in general terms, how often do these x-intercepts occur? Sorry, what did you say?
You said the same thing.
You said it at the same time, so I can, yeah, every pi. Good, so we're going to add pi n, where n is an integer. Now, if graphing isn't your thing, then what you could do is just go second sine, 0, and you'll get 90 degrees. Okay, but then you have to kind of have a bit of knowledge of the graph that every 180 degrees that solution is going to exist. Okay, so you can start by finding a reference angle, but you will need the graph to figure out how often it's coming up. Part B, if you were to graph the left-hand side as your y1 and the right-hand side as your y2, you'd see the similar thing as what we saw before. The graphs look the same, but there's hidden restrictions. There's hidden little holes in that graph. Okay, so unless you use zoom trig, you're not going to see those holes. You have to be very, aware of what you're dividing by. Okay, so if you were to graph, y1 would be your left-hand side, 1 over cosine x minus cosine x. y2 would be sine x and tan x. And graphs would appear to be the same. Okay, I'm putting a big but here, so graphs would appear to be identical, but be aware of the restrictions that we just saw in part D.
So both graphs have the same restrictions of two. They both have cosets on the bottom.
I guess in this case, yeah. In some cases, like the first example,
Yeah.
you wouldn't necessarily have that,
Mhm.
but in this case they do.
Okay.
Yeah. Okay, that's a general note for other questions then. Part C, I'm sorry if I just mixed the order here. Verify the statement is true for x equals pi over 3. I meant to do that part A, didn't I? Okay, so if we use x equals pi over 3, then on the left-hand side we'd have 1 over cosine pi over 3 minus cosine pi over 3. And if you evaluate that, you'll get 1 over a half minus a half, and go further, you'll get 3 over 2. Now, this you can just calculate cos pi over 3, you're going to get a half. Okay, cos pi over 3, you're going to get a half. Or you can remember those special triangles. Okay, pi over 3 is 60 degrees. Unit circle, radius 1. Okay, we're going to have 30 degrees up here. So we have root 3 over 2 as our y, and 1 over 2 as our x. Now, just a reminder, cosine is x over r. But our r is 1, so we don't need it. It's just going to be your x coordinate, which is 1 over 2. Okay, if you don't feel like memorizing the special triangles for this, no problem. Just go cosine pi over 3, and you will get 1/2. So we have 1 over 1/2 minus 1/2, and you get 3 over 2. Okay, right-hand side, sine x, tan x, where we have pi over 3. So sine pi over 3 and tan pi over 3. Now sine pi over 3, that's just the y coordinate for 60 degrees, so root 3 over 2. We're going to multiply that by the tan pi over 3, which is opposite over adjacent. So root 3 over 2 divided by 1 over 2, what's going to happen to these twos? Cancel out. So we have root 3 over 1 is just root 3. Root 3 times root 3 is 3 divided by 2. Now, I'm showing a little bit more work than you would need to do on this. If you just put in your calculator sine pi over 3 times tan pi over 3, you would get the same. Okay, so for just that x value, pi over 3, we've proven the identity to be true. Okay, but it's really important to note that although the identity proved in this section as well, we still have some restrictions. So some values might be true, some values will not be true. Okay, so always check for those restrictions. Alright, another suggestion for proving identities is to factor. That's going to be a step that we'll use this time. So on the left-hand side, that looks most complex to me. So we'll start there. We have sine x cosine x squared plus sine x squared, or cubed, sorry. Now my hint is we have to factor. What could I factor out? What's that? Sine x, good. We're going to take out a sine x, and that leaves us with cosine x squared plus sine x squared. Check out the identity board. Do you guys see an identity that I could plug in now?
Wait, how did you? Oh, wait, why does the cosine change? Factor.
Sorry?
Oh, never
So
mind.
basically
Never mind.
factoring is like
I
division.
see,
So I've divided sine x out of here, and I'm
Yeah.
left with cosine x squared. Divide by sine x here, and you have sine x
I
squared.
thought you put sine x cubed again.
Oh, okay.
That was fine, yeah.
Just a 2. Okay, so do we see an identity that could replace cosine x squared plus sine x squared?
Pi that I
Good, the Pythagorean identity. So we have sine x now multiplied by 1. Because I'll just go over here and show you guys. Sine x squared plus cosine x squared equals 1. Okay, so that's an identity you'll have to be able to spot or memorize. So when we multiply through, we just are left with sine x. Right hand side, 1 over cosecant x. What's the reciprocal of cosecant? Sine. So I could write this as 1 over sine, or I just know that it's sine x.
It's just the reciprocal of sine.
Okay, so the reciprocal of cosecant is 1 over sine. And if I were to multiply by the reciprocal in the numerator and denominator, I would just end up with sine. Okay, so right hand side equals left hand side. We've proven the identity. But now we have to ask, are there any restrictions? We're dividing by cosecant x. So that means that cosecant x cannot equal 0. But cosecant x is actually like 1 over sine x. So 1 over sine x can equal 0. And we're dividing by sine x, so in summary, sine x cannot equal 0. So maybe you've memorized the x-intercepts of sine, maybe not. Let's just draw the graph. Starting at the x-intercept, working our way up and back to the midline. So we have x-intercepts at 0, at pi, and at 2 pi. So every pi times n, I have a solution. And if I'm dividing by sine, that means it's my restriction. So x cannot equal pi n, where n is an integer. How are you guys feeling so far? Any questions? What we've covered? Trust me, the more practice you do with this, the better.
If you look up that stuff in front of you, it's pretty easy.
Yeah, you'll probably just want a formula sheet in front of you to start, and then eventually you're just going to memorize them. Okay, let's try another. Sine A plus tan A over 1 plus cosine A is equal to 1 over cotangent A. So I think it's pretty obvious the more complex side is the left-hand side, so let's start there. Okay, just taking a look at that. One of the hints is that we need to write the terms in reference of sine or cosine. So is there anything there that we could change to put in terms of sine and cosine?
Is it, you use like a quotient identity?
Good. So we're going to take tan A and we're going to use the quotient identity and it will become sine A over cosine A. Okay, so quotient identity for tan A. And we'll get sine A plus sine A over cosine A. All over 1 plus cosine A. So step 5 of the hints, do you have to take off early? Okay, see you later. So step 5 of the hints is that if you have any sum or differences, that you basically need to use a common denominator to combine them. Okay, so we have sine A plus sine A over cosine A. We need a common denominator for the next one. Next step. So I'm pretty much just gonna rewrite what we had, and then I'll apply a common denominator. So in the big numerator here, if I need a common denominator, I have to multiply by cosine A, and whatever I do in the denominator, I also do in the numerator. Then I'm just going to clean things up. So I have cosine A sine A plus sine A all over cosine A, and all of that over 1 plus cosine A. So I've just combined these numerators here, and the denominator is just cosine A. Nothing has happened with 1 plus cosine A ever since we started. I've just rewritten it every single time. Okay. We have two terms that have sine in both of them, so the next step is we're going to factor out sine. We'll end up with sine A multiplied by cosine A plus 1 divided by cosine A divided by 1 plus cosine A. I'm just going to do a quick little side example, and hopefully you guys can catch on quickly, and I'll show you how we cancel something out very easily. So if I had AC divided by B, all divided by C, what I could do is make this denominator C over 1. Okay, and to get rid of this denominator, I have to multiply by the reciprocal, 1 over C. So these cancel out, but whatever I do in the denominator, I must do in the numerator as well. So I'm going to multiply here by 1 over C. What happens to these C's? They cancel out. So I'll just remind you what we started with. AC over B all over C. These C's canceled out. Do you see anything in common in this numerator and this numerator? Cosine A plus 1s, right? So those cancel out. Do you guys want me to repeat these steps? You got it? Alright, so now we are left with sine A over cosine A. That's my left-hand side. And my right-hand side, we started with 1 over cotangent A. We need them to look the same. What can I do with 1 over cotangent? Yeah, perfect. The reciprocal of 1 over cotangent A is just tan A. And what's the identity for sine A over cosine A? Tan A. So there's one of two things you could do. You could leave it as sine A over cosine A and then just keep going with this. Sine A over cosine A, and you'd have the same sides. Or you could convert this to tan A and then just be done.
Well, do they usually want it in simplest form?
Typically they'll say if they want it in terms of just sine and cosine.
Oh.
And if not, then you'll want to put it in simplest form. Okay? But just be aware, if this was a multiple choice question, you want to be on the lookout for sine A over cosine A or tan A. Okay? If they say the most simplest form, tan A. Okay, so what are some non-permissible values? Well, we have to go through that entire left-hand side again and look at what were our denominators, and then look at the right-hand side and what were our denominators. So we get to dissect a little bit. Step 1, what's our denominator? 1 plus cosine A. So 1 plus cosine A cannot equal 0. It's one of our restrictions. Okay, then we go here, to here, to here. Denominator is cosine A. So cosine A cannot equal 0. Let's just see if there's any more from the left-hand side. Cosine A, 1. No. So from the left-hand side, these would be our restrictions. Now let's look on the right-hand side. 1 over cotangent A, we have a denominator. So cotangent A cannot equal 0. So let's just work through each of them and we're going to figure out what are the values of A that are our restrictions. I'm just going to start with the one that we've been doing kind of over and over again. So cosine A cannot equal 0. Hopefully you guys have memorized it now. What would be the solutions of cosine normally?
1
Pi over 2 plus pi n, right? Okay, so that means A cannot equal pi over 2 plus pi n, where n is an integer. Okay, we've been doing that a few times. Okay, when in doubt, just graph cosine, find the x-intercepts. Those are your restrictions. You need to put it in the general terms, though. Okay, then we'll go up top. 1 plus cosine A cannot equal 0. So first, let's just isolate the cosine A. Cosine A cannot equal -1. So we'll find our reference. A cannot equal second cosine -1. When you guys calculate that, what do you get? $180 or pi? Okay, well, cosine, let's just draw this. Whoop. Now 180 degrees or pi, we're at -1. So how often would that occur? Every period. So every 2 pi. Okay, so we have pi plus 2 pi n, where n is an integer. Okay, so I find it always helps to just draw a little picture. Okay, and then lastly, we have cotangent A cannot equal 0. Well, cotangent A can be rewritten as cos A over sine A. And because cotangent was in the denominator, that means that cosine and sine are restrictions. So we branch off again. And we would say that cosine A cannot equal 0 and sine A cannot equal 0. Now, have we already done the cosine one? Right here. Yeah. Okay, so we just have to do sine now. Okay, and if we draw the graph of sine, we have 0, pi, and 2 pi would be our solutions. So every pi we have a solution. So A cannot equal pi n. Okay, so those would be our restrictions. Any questions so far? I feel like you guys are like it's pretty quiet.
When you did the cosine 1 plus cosine A1,
Yeah.
why? So that next point there,
Yeah.
would that be at 540?
Yeah.
Okay.
So So basically we're at 180 plus 360, and then plus 360, plus 360, plus 360.
Okay.
Alright, yeah, we still have time. So now we're just gonna graph these. Okay, so first graph will be the left-hand side. Domains between 0 and 2 pi, so we'll just keep it in radian mode. My calculator always quits on me. So we have sine A for x plus tan x divided by, and I'm going to put this all in brackets, 1 plus cosine x. So you'll notice I put the entire numerator in brackets and the entire denominator in brackets. And because I reset my calculator, I just have to change the window settings. 0 to pi. And what's it going up by? 45? No. 90? So if you guys just need a little help with the scale, this is what I put. Whoa, can't really see that. Okay, so 0 to 2 pi, scale of 90 for pi over 2, and then negative 3, 3, and 1.
Driver's not working. I was just deciding what to eat. You're right. I guess you made my decision for me. Thank you.
Alright, so let's
I'm
drop
driving
it
down.
down.
Which year was that? Even
So what graph does this look similar to?
tan.
Tan, which makes sense because when we simplified both sides of the identity, it simplifies to tan, right? So now we just have to note what are our restrictions. Okay, so let's just start by drawing this out. Okay, I put the same scale as what's on your picture. So at 90 degrees, we have a restriction, and that makes sense if we look here, right? 90 degrees was one of the restrictions, then every 180, we're going to have another one. So if that's 90, okay, another 90, another 90, that's 180. We've moved over. We have 2 restrictions. So pi over 2, 3 pi over 2. And we'll just follow the graph of time. Okay, so we've satisfied pi over 2 plus pi n. And just keep in mind for this side of the equation, we got these 2 restrictions. Okay, so 1 plus cosine A couldn't equal 0. We found a restriction of pi plus 2 pi n. So let's just work those out. Okay, so pi, if there's a restriction here, we have to put a hole. And then keep in mind the period of tan is 180. So to get to this next one.
Good afternoon, Mountaineers. Here are your announcements.
A happy birthday over the break to Taylor Trustwell, Caleb Edwards, Tyson Upper,
Emerson Gauthier, Mary Peltier, Dylan Stegeson, Dylan B. Justin Spatafor, and Claire Stewart. Have a good afternoon, Mountaineers.
That's okay.
We still have 3 minutes, so let's try and get through this one graph. I'm just going to keep drawing on this side too.
Thanks, Emma.
What I'm here for, Chris. Okay, so at pi over 2 we have a restriction. Okay, and then if we look at the first one at pi, we had a restriction. And then every 2 pi times n, we have a restriction. So would there be a restriction right here? Have we added 2 pi to get to this next marker? No, we've just added pi, so that's not a restriction. Okay, this one would not be a restriction because we've only gone over pi. But if we go over pi, 2 pi, we'll have our next restriction. Okay, so it's really important to note that these restrictions came from our left-hand side, and that's what we're going to be graphing. Whereas on the right-hand side, we still have the graph of tan A, right? But we have a restriction every pi n. So if I were to just draw it on this picture here, basically I have a hole here, here, here. Okay, every x-intercept has a hole. And then tan generally will have a restriction anyways for the asymptote. Okay, take a look here. This came from our right-hand side. The restriction is pi n. So every pi plus another 180. This is pi. Okay, plus another 180. Plus another 180. We're going to have holes in the graph. Okay? Does that make more sense if I draw a line?
Why didn't you draw that on the board? Like you didn't put a hole on the...
So on this one, that's just the left-hand side of the identity. And for the left-hand side, we found restrictions pi plus 2 pi n. And we found restrictions pi over 2. I'll go through it tomorrow just to polish it off a little. Okay.